Yeah, no. Now you guys can see me clearly, see the slides and listen to me clearly. Clearly. Okay. So only 12 students are online at the moment. Can you hear me and you can see the slides as well? Okay, that's good. So today we are going to start from the transmission electron microscopy. And even yesterday students were asking, sir, is it tunneling electron microscopy? No, it's transmission. This is a mistake in this, PDF slides. Within this slide, this is a mistake. I already had corrected. If you see on this comment, it's written transmission. It's not tunneling. It's been corrected to transmission. Okay. You click on this message and you will see transmission. Okay, it's transmission. It's not. So it's been written clearly that it's transmission electron microscopy, not tunneling. Okay, so is it fine if we can start now? You guys are okay if we can start lecture now? Yes, so we can hear you and see the slides as well. That's good. Very good. Okay, so you guys don't want to wait for other students to come and join. I think we should start now because it's already 9:35. So better to start. The other students, as they come, they will join us. Okay, the first electron microscope. First of all, TEM. TEM stands for transmission electron microscope. I repeat, TEM stands for transmission electron microscope, not tunneling. It's transmission electron microscope. Okay. The first electron microscope was built in 1932 by the German physicist Ernst Ruska, who was awarded the Nobel Prize in 1986 for its invention. Okay, the first commercial TEM was available in 1939, and the resolution was about 1 nanometer. it could see up to 1 nanometer, and the typical acceleration voltage was 100 to 400 kV, 100 to 400 kilovolts was the accelerating voltage in this transmission electron microscope. And some of the instruments of TEM, the accelerating voltage exceeds to 1 to 3 megavolts. So it's much higher than kVs, 1 to 3 megavolts. Okay, the basic principle, you can see here, it's very clear from this one. We have the electron gun. It's similar to the, I told you earlier, it's similar to the SCM. We have electron gun, primary electron beam comes from here. And then secondary electron detectors, X-ray detectors, these are embedded, backscatter electron detector, these are embedded in the TEM as well. And then we have bright field, dark field images. So, you know, it's not that simple like SCM. So it's a bit complicated compared to SEM. But we have a similar, you know, geometry. You can see this one is more clear. You can understand everything from here. This is the electron source at the top. We start from the top, electron source, and then the first condenser lens. It condenses the electron beam. It converges it to one point. Secondary condenser lens, and then the objective lens. The specimen is put over here, and then the image is formed at the bottom right here. Then the projector lenses as well, diffraction lenses as well. So this is a complex geometry, you know, and the final image is formed right over here on the screen. This is the projection chamber. Fluorescent screen is right at the bottom. You can see over here. So it's almost similar in a sense that it has the same electron gun. It generates a beam of electron and it passes through these lenses and is converged onto the specimen. And the electron beam passes through the specimen and forms the image. It may be bright field or it may be dark field. Okay. So you can see here the parts, what they're saying. First of all, condenser system. What is condenser system? Lenses and apertures for controlling illumination on the specimen. And objective lens system, image forming lens, limits the resolution. Aperture controls imaging conditions. And projector lens system magnifies image or diffraction pattern onto final screen. It's to, you know, magnify the final pattern on the final screen. Okay, and then there are intermediate lenses as well. And intermediate lenses function is to transmit or magnify the enlarged image. So these are the important parts of the TEM, transmission electron microscope. And you guys can see here, it's different parts and how the electron beam is first, you know, converged and then directed onto the specimen, and it transmits through the specimen, forms a final image. So the design of transmission electron microscope team is analogous to that of an optical microscope. In TEM, high energy greater than 100 kilovolts electrons are used instead of photons, and electromagnetic lenses instead of the glass lenses. So that's the main difference between an optical microscope and transmission electron microscope. The electron beam passes an electron transparent sample and a magnified image is formed using a set of lenses. This image is projected onto a fluorescent screen or CCD camera, closed circuit camera, whereas the use of visible light limits the lateral resolution in an optical microscope to a few tenths of a micrometer. The much smaller wavelength of electron allows for a resolution of 0.2 nanometer. So this is even higher. It just claims 1 nanometer, but the recent model, the updated model TEM, they have resolution even higher than the previous one. So it has a resolution up to 0.2 nanometers. Okay, you can also click on this message as well and see. Fundamentally, a charge coupled device CCD is an integrated circuit etched onto a silicon surface forming light sensitive elements called pixels. Photons incident on the surface generate charge that can be read by electronics and turned into a digital copy of the light patterns falling on the device. This is what CCD stands for. Okay, because this term is used, CCD, and this is what CCD stands for. You can see the detail from here. Okay, what actually is happening on the surface? This is, for example, your sample or the specimen. The incoming electrons fall on the sample or the specimen, and then there is secondary electron scattering. There is cathodoluminescence, X-rays happening at the same time. Auger electrons are emitted from the surface. Backscattered electrons are also emitted from the sample or the specimen. And then there is inelastically scattered electrons, unscattered electrons that pass straight through the sample or the specimen, and inelastic scattered electrons. So all these phenomena are happening at the same time, but we are interested in the unscattered transmitted electrons because this is transmission electron microscopy and it's based on the transmitted electrons. However, the rest of the electrons that have been reflected or or scattered elastically or inelastically, there are also detectors embedded in the TEM to study various parameters and various features using these electrons as well. So, but mostly we are interested in the transmitted ones. Okay, for the imaging, here you can see the image. This is the TEM image, and you can see here high resolution TEM image of a multi-carbon nanowire. Okay, this is carbon nanowire and multi-wire. The wire consists of segments bounded by inner segment boundaries, and this is from 2008 Philips Electronics N.V. So this is the courtesy from these people, and we use this image to explain how the TEM image looks like. Okay, so this is the scale you can see, and this is the carbon nanowire. Okay, you can see multi-wall carbon nanowires, because from here it is clear that there are walls-like structure. There's a bright, transparent, and then there's light black wall-like structure. So this is carbon. This is nano-carbon nanowire. Okay, so its dimension is in the nanos. Okay, then you can go through the theory of this. There's small formulas about its radius, how the radius is found. Okay, spherical aberration, because there's aberration in the TEM as well. How the image is, resolved and made clear. You guys can see this feature as well. And then there is, this 3D. Okay, we can go to this tomography. This is also available in the latest TEM. This feature is available in the latest TEM. Initially, it was not available, but nowadays, in the latest TEM, this feature is also added. TEM tomography involves the acquisition of a large series of images at many tilt angles. Okay, it's like CAT scanning and MRIs. They have images at different angles of the sample with respect to the electron beam, in analogy to the CT scanner used in medical diagnostics. The acquired data series is reconstructed into a 3D representation. This technique is especially useful in case of studies of three-dimensionally shaped objects, such as layers in small pores and 3D shapes of small objects. So this looks like a wire. Okay, this is nanowire-like structure. The three-dimensional reconstruction of the morphology of a part of a gallium phosphide, gallium arsenide heterostructure nanowire. So this is the kind of nanowire and having a diameter around 40 nanometer. So it's been constructed, and the image, this kind of photography in the TEM is known as tomography. Okay, bright field and dark field image contrast. Okay, for the bright field contrast formed directly by occlusion and absorption of electrons in the sample. Thicker regions of the sample are regions with a higher atomic number will appear dark, while regions with more sample in the beam path will appear bright. Hence the term bright field. Okay. Okay, we go through again. Regions with a higher atomic number will appear dark. Okay, regions with higher atomic number, they appear dark, while the regions with no sample in the beam path will appear bright, hence the term bright field. And in the contrast, dark field image formed by incident electrons that are scattered by the atoms of the specimen elastically. These electrons can then be collected using magnetic lenses to form a pattern of spots. Each spot corresponds to specific atom spacing or plane. This pattern can then yield information about the orientation, atomic arrangements, and phases present in the area being examined. Okay, so these two fields are being used, dark field image and bright field image. Okay, then there is sampling, how the sample for the TEM is prepared. This is also, a very tedious job. The higher the resolution, the smaller the analyzed volume becomes. Okay, so this is the most important sentence in this. The higher the resolution, the smaller the analyzed volume becomes. Drawing conclusions from a single observation or even a single sample is dangerous and can lead to completely false interpretations. Okay, and then interpreting transmission images, 2D images of 3D specimens viewed in transmission, no depth and sensitivity. This may also be the issue. Electron beam damage and safety, particularly in a polymer and ceramics. The high energy of the electron beam utilized in electron microscopy causes damage by ionization, radiolysis, and heating. Okay, these are the damaging parameters. Specimen preparation thin below 100 nanometer. The specimen prepared for analysis should be less than, thickness should be less than 100 nanometer for the electrons to transmit through these samples. Then there are different kinds of TEM, cryo-TEM, okay, in which the vacuum is created through cryo pumps, liquid nitrogen, etc. Half energy filtered TEM, EF-TEM. Okay, so these are various type of TEM. HARP stands for high angle annular dark field imaging, and energy filtered TEM, EF-TEM. So you guys go through these, SEM versus TEM. There are some points you guys can read through these. And here's a comparison, TEM and SEM comparison. You guys can see from the images. This will further, clear your concepts about how the SEM and TEM works. I think you guys understand tomography now, isn't it? For tomography, various images are taken at different angles and then they are plotted, and to form the 3D image. Just like in CAT scanner, you guys maybe have seen the CAT scanning image from the medical diagnostics. So in a similar fashion, a TEM processes the images at various angles for a specimen and then forms a 3D image. That is called tomography. Okay, EELS is energy electron energy loss spectra. EELS. EELS, did we go through EELS? Wait a minute. EELS image, we still haven't gone through, I think, EELS image. But EELS stands for energy electron loss spectra. Okay, for EELS, you guys can understand that in case of EELS, we have, we detect the element from its electron energy loss spectra. There is a spectrum, and for a specific energy loss from an electron, it corresponds to a specific level of energy. And from that specific level of energy, we can detect where the transition was. And it, help in identifying the element and also identifying the planes from where it was transited. Okay, for AFM, next is AFM. Okay, we go to the AFM basic diagram, and then you guys understand the principle. Okay, this is the basic diagram. If you guys understand this diagram, you guys can easily understand the principle of AFM, atomic force microscopy. Okay, in AFM, you see There is a nano tweezer, this one, and there's a light source from here, and here is a mirror, and photographic film is over here. Okay, this is the nano cantilever. It moves over the surface. This is a moving state. It moves over the surface and detects the surface atom by atom. And this is the light as it goes on the, for the atom. If there is like a hilly structure, it goes up. Okay, and if there is some depression, it goes down. So a light is falling on the mirror, and this mirror light is reflected and falls on the photographic film and forms an image. So from that line, from that curvature, you guys understand where the atom is and where the depression is. Okay, now we read this. Atomic force microscopy is to investigate the electrically non-conductive materials like proteins, etc. In 1986, Binning and Quaid demonstrated for the first time the ideas of AFM, which used an ultra small probe tip at the end of a cantilever. This one. This is the small probe tip at the end of a cantilever. This is published in Physics Review Letters in 1986. And in 1987, Vikram Singhe et al. Developed an AFM setup with a vibrating cantilever technique. And it was published in Journal of Applied Physics 1987, which used the light lever mechanism. Okay, it is further elaborated in this diagram how this is all this data from the cantilever, and this is the mirror. This was projected into the position sensor photodetector, and this was then rectified, and the error was removed and then processed to the computer. And then piezoelectric scanner, it projects plots all the data on 3 dimensions, and you can see the graph clearly. Okay, then you guys can go through the further detail of EFM. This is how it is happening. This is the tip, narrow cantilever, and it touches the surface. There could be 3 different modes. In the contact mode, left, the deflection of cantilever is kept constant. And in non-contact mode, right, the tip is oscillated at the resonance frequency, and the amplitude of the oscillation is kept constant. And then there is tapping mode. It's like you tap the surface at some points, somewhere between the contact and the non-contact mode. So this is called the tapping mode. Okay, so further detail you guys can see here, and there's some points, advantages and disadvantages, and then the AFM images, 3D, tapping mode, contact versus tapping mode. It's comparison. You guys can see here how the AFM image looks like and how the surface is. You guys can see that there are some hill-like humps, and then there are depression as well in the image. So you guys can see it clearly. So then there's some comparison as well, SEM, TM, and AFM. And you guys can, once you understand the principle, you guys can easily elaborate these different tools and see the comparison between them. So tomography clear. Okay, so any further question you guys can ask me. And now it's almost 30 minutes video already. So if there is any question, you guys can ask me. I can take only 1 or 2 questions. And if there is no question, we can end this lecture here. And Assalamu alaikum and Allah Hafiz. Till the next lecture. Yes, Rana Muhammad Raza. You have any question? Yes, Mr. Rana Muhammad Raza, you just typed, sir. And do you have any question? STM explain. Oh, okay. STM, is scanning tunneling microscope. Scanning tunneling microscope also uses a nano cantilever, but it is multifunctional. It can move one atom from one point and it take it to some other point as well. That's the feature of the STM. I told you earlier, STM can lift even a single atom and it can move, manipulate the atom as well. STM is a very versatile, and it's a super duper tool. It's very expensive, and it can view the atoms and it can also move them from one point to another. This was already covered in the first lecture, and I have repeated that lecture number of times. So I have repeated again. What is STM? Is scanning tunneling. It uses the phenomena tunneling. It lifts one electron with attraction of the atom of the cantilever, nano cantilever. It's a tip-like structure, and it lifts one atom and it can place it on another point. And then there was one video, a boy and his atom. I have shown that video a number of times since the start, and I think if you guys can see that clear, you see that video, this concept will be very clear to you. You go to my YouTube channel and you can find that video. That video is very important, and you just click on a boy and his atom and you can see that video. That will further clarify your concepts. Okay, so with this we end today's lecture, inshallah. Any question, any problem or issues, we can discuss in the next lecture. Till then, take care. Assalamu alaikum and Allah Hafiz.